Hi, my name is Tu, and thank you for being here with me today. Today, I would like to present our recent work, which is HyperTP, a solution for reducing the vulnerability window of hypervisors by replacing one kind of hypervisor with a completely different one. So first, one thing about large data centers is that you cannot afford to bring down whole system. So most of the time, you need to perform live migration to upgrade your hypervisors. And as you can imagine, this method uses a lot of computing resources and bandwidth, and in fact can be very slow. So Alibaba, for example, reports needing 15 days just to patch one cluster in the public cloud. And this time window is long enough for attackers to exploit and break into your system. That's why the main idea of our work here is to move a running VM from one hypervisor to another, for example, from Zen to KVM, and we call that hypervisor transplant or HyperTP. Our idea here is that we have a large pool of different hypervisors, and by switching between them, we'll be able to adapt our attack surface to any emerging vulnerabilities. And HyperTP is also helpful for data center operators because they're no longer locked to one single hypervisor, and we'll be able to choose between multiple of them without having to worry about the migration path from one to another, especially if you manage the VM using an abstraction layer like libvirt or OpenStack. So you can imagine the following timeline of handling a security issue. Previously, your best choice to deal with any vulnerability is to wait for a security patch. But with HyperTP, switching to another hypervisor lets you mitigate the vulnerability while you're waiting. So you have the choice to return to your original hypervisor once it's fully patched. So in general, what it does is that it shrinks the vulnerability window of the system, as you can see on the figure here. So for HyperTP, our solution is a combination of two approaches. One is that you directly replace the running hypervisor with another while preserving a VM on the same host, and we call that in-place hypervisor transplant or in-place TP. Another approach is that you migrate the VM that is running on the source hypervisor to a different destination hypervisor on another host. This is similar to live migration, so we call that approach migration-based transplant or migration TP. So both of these approaches depend on a couple of main principles. The first one being memory separation or classification of memory types of the VM, and the second one is an unified VM representation across all hypervisors. So here I have the main workflow of HyperTP, which consists of 5 steps. Firstly, you need to preserve the VM state and memory of a running VM that you want to transplant, and suspending it at the same time, which are steps 1 and 2. Next, you transplant the VM to the new hypervisor, either using the in-place technique or the migration technique. Once the transplant is done, you restore the VM state and resume its operation. For the principle of memory separation, we identified 4 categories of hypervisor memory. These categories range from the most VM-specific states, like guest memory, which does not concern the host, then the states that partially involve the host, like VM memory maps, and also there are states that are hypervisor only and not related to VMs at all. We identified that the first 2 categories of states are needed to reconstruct a VM on another hypervisor, so these 2 categories need to be saved and translated in HyperTP. So next, we identified that on the same host, the states of running VMs tend to have elements in common with each other, even across different hypervisors. This is because these hypervisors can either use hardware virtualization, which actually enforces this commonality, or there is a common API like virtio, which is shared by multiple implementations. From the viewpoint of the VM also expects a common hardware interface, for example, things like timers, interrupt controllers, and so on. So with each of the device, we implemented a pair of functions to translate them from the hypervisor state into a format of our choice. And finally, we can extend this kind of representation into you can call it an unified virtual machine API that can be used by any guest kernel on any hypervisor. So for our actual implementation, we based it on Zen and KVM. For KVM, we focused our implementation on top KVM tool, which is a lightweight utility for running virtual machines on top of KVM. Overall, we implemented HyperTP in about 8,500 lines of code, of which around 90% is based in user space. So this leads to a very flexible implementation that also minimizes the security impact of our solution. For in-place TP, we implemented it from Zen to KVM and from KVM to Zen, as well as from Zen to Zen, which you can use for upgrading from one version of Zen to another. For migration TP, we also have an implementation for moving from Zen to KVM. So next, I'll be talking about how the components of HyperTP are done in detail. So first, let's go into devices. Actually, saving and restoring virtual devices is already part of most hypervisors. So what we needed to do was just to adapt these hypervisors to use the same device format. So we ensured that the critical platform devices are preserved, and then for any devices that are not compatible with the new hypervisor, we unplug them before performing the transplant. However, like what I mentioned for the unified VM representation, these devices can be eventually integrated as part of an uniform virtual machine API that is consistent across many hypervisors. So during hypervisor transplant, besides saving guest state, we also need to take care of guest memory. In the particular case of in-place TP, we don't want to save this guest memory to disk because it would take a long time to save everything. So instead, what we do is we try to keep all guest memory pages in host RAM so that these pages can be reused by the next hypervisor. And what we did is we used an in-memory file table structure to keep track of these pages and represent each VM's memory as a separate file. We call these metadata table pages PRAM, and the way we construct the PRAM pages is that first of all we allocate some temporary memory. We then define some regions of physical memory that must be preserved in the host, and then copy any VM memory that's living there into the temporary region. We finally use the remaining temporary memory to construct a PRAM table for each VM. So this is the structure of the PRAM table. It starts with the PRAM pointer value that points to a chain of root directory pages, which I've colored in red here. Each root directory page contains 5 pointer entries that point to file info pages, which are colored in green in this figure. Each file info pages themselves are like inodes, and they contain the metadata of the VM memory file, including its size, file mode, file name, etc. Each file info page also contains a pointer to a chain of nodes, each containing page entries which I've highlighted in blue here. Each page entry finally is the guest physical to host physical mapping of a memory page so that this mapping can be restored in the new hypervisor. So now that we have constructed the memory structures, I would like to proceed with the third step, which for migration TP is just like normal migration. But for in-place TP is a bit more tricky, which is you have to replace the running hypervisor. So while we replace the hypervisor, we don't want to lose the existing memory content that contains the VM memory. So we use kexec to boot the new hypervisor without going through BIOS. We made some fixes for this kexec feature so that we can boot smoothly from Zen to KVM and vice versa. Also, we pass the PRAM table address using the kernel command line to the new hypervisor so that it can be processed. So once the transplant is complete, we have to start the step of restoring the VM on the new hypervisor. We added code in KVM tool to map each VM state between Zen's VM state and KVM, and then we restored each device with the corresponding mapping. So during this process, we also had to make sure that the structures of the virtual devices on both sides matched up with each other. For example, we had to make sure that the number of virtual I/O APIC pins on both sides matched up, and to make sure that devices like virtual clocks would continue to function after the transplantation. Aside from the VM device states, we also needed to restore memory of the VM. In the case of in-place TP, the new hypervisor parses the PRAM structure to detect the existing memory regions and present them to the new VM being restored. For KVM, we present the PRAM memory as a file system so that the new VMM like KVM tool can just mmap the file and have the memory ready for use. But for Zen, we had to implement new hypercalls to traverse this new PRAM file system and assign these files to the memory of domains that need to be restored. And that's all the steps of hypervisor transplant. So we evaluated HyperTP on 2 machines that we call M1 and M2. Since we have quite a few different transplant cases that we needed to examine, here I will go into detail the case of Zen to KVM transplant. Here's a figure that tells you how long each step of the process takes for a VM with 1 vCPU and 1 GB of RAM. You see that for M1, the time for transplanting this VM is only 1.7 seconds, which is to say after 1.7 seconds of downtime, the VM is already resuming its operation. For M2, the transplant time takes a bit longer, which is around 3 seconds. For some devices, it takes more time to restart. For example, the network card on M1 takes around 8 seconds of downtime before it can be resumed. But we also implemented some fixes into a Linux kernel to allow fast resumption of devices. For example, the RAID card, which normally would take around 30 seconds to a minute to start, and we hold up the entire boot process. With our patch, the RAID card can be resumed right away and will not hold up the process. Here we have a figure of Redis performance under in-place TP and migration TP to show the impact of the two solutions. The left side is comparing in-place TP to a normal VM running on Zen without any transplantation. We see here that with in-place TP, the process starts and then 9 seconds later, the VM resumes, and you don't see any impact to Redis performance before or after the transplant. On the right side with migration TP, you can see that regardless of whether you're doing Zen to KVM or normal Zen to Zen migration, the performance is the same. In this case, the Redis server had bad performance for 76 seconds, as well as a short period of downtime before everything goes back to normal. So we can see how a solution like in-place DB can speed up the process of patching of a data center, since you spend much less time on migrating the hosts and all of the VMs get transplanted at the same time without consuming any network bandwidth and doesn't have a long period of impacting performance. So the factor of impact on upgrade is also something we consider for our solution. We use the tool called Better Place to simulate the upgrade of a cluster which contains a number of VMs. In the cluster, you can denote some VMs as being compatible with in-place TP and some others as not compatible. We set up the upgrade process so that you can migrate the VM from one kind of hypervisor to another. It can be from Zen 2 KVM or Zen 1 to Zen 2, for example. In any case, you can see that the more VMs that we have that is compatible with in-place TP, the more time you save in upgrading the hypervisor cluster. So if you have 80% of your VMs that are compatible with in-place TP, for example, you save 80% of time upgrading the hosts, and this is with all hosts having 10 gigabit Ethernet. With this, you can see how HyperTP will help shrink the vulnerability window of a data center by helping you speed up the upgrade process. And that's it for the presentation of HyperTP. Thank you very much for listening.